On the night of 2-3 February 1943 near Rotterdam, a short Stirling of Royal Air Force Bomber Command was shot down, and its H-2S radar set was recovered, an incident that prompted immediate technical exploitation by German specialists. H-2S Mark I entered service in late January 1943 and provided Bomber Command crews with a ground mapping aid for night navigation and target finding. But once a set fell into German hands, it also posed a serious technical problem and a strategic question for Luftwaffe planners. The captured equipment was transported to German technical teams and dissected in detail, yet even as engineers mapped its circuits, they recognized that wartime shortages of specialized components, skilled labor, and precision machine tools, together with bomb damage to factories, would limit any rapid scale-up. Bench tests and engineering appraisals showed that the Magnetron alone could not deliver an operational centimetric radar capability. Turning this single device into a reliable service set would require new receivers, aerials, displays, power supplies, and production lines, and there was not enough time to build them at scale to negate Allied centimetric advantages before the war ended. The recovery of an H-2S set from a short Stirling wreck near Rotterdam on the night of 2-3 February 1943 presented German engineers with an urgent technical challenge. The cavity magnetron, operating at centimetric wavelengths around 10 centimeters, demonstrated an Allied centimetric capability that exceeded the resolution of Luftwaffe metric and decimetric systems. H-2S enabled Bomber Command to map terrain for navigation and target identification at night and in adverse weather. That capability, therefore, posed a significant operational challenge for German night defense and required prompt technical examination and assessment. German radar doctrine in 1942-43 had prioritized longer wavelengths in the metric and decimetric bands, favoring established systems such as Freya and Würzburg. So the appearance of an Allied centimetric set forced a reconsideration of whether and how such shortwave capability could be integrated into Luftwaffe operations. Telefunken teams dissected the recovered H-2S in late February 1943, replicated the Magnetron in principle, and built trial assemblies around it, but scarce high-grade materials demanding precision manufacturing and bomb damage. To industrial capacity, all limited the speed with which any German equivalent could be produced. Bench tests and engineering appraisals made clear that the Magnetron was central but not sufficient. Without a coordinated program to design the associated systems and mass-produce complete airborne and ground sets, Germany could not hope to overturn the Allies' centimetric advantage before the war ended. The H-2S radar salvaged from a short Stirling's wreckage near Rotterdam on the night of 2-3 February 1943 lay on Telefunken workbenches by late February. German engineers assigned to assess its centimetric capability confirmed the cavity magnetron as the core of the set, operating at wavelengths around 10 centimeters. This compact high-peak power source enabled Allied bombers to map terrain for navigation and target identification at night and in adverse weather, and it required immediate technical examination. German radar practice in 1942-43 prioritized metric and decimetric bands suited to broad aircraft detection, but not to fine ground mapping. The H-2S set's centimetric pulses produced shorter wavelengths and finer resolution than systems then in German service. The captured equipment therefore posed two problems at once: whether the magnetron and its associated chain could be reproduced, and how such capability could be integrated into Luftwaffe operations. Telefunken teams dissected the set in late February 1943, with initial exploitation meetings recorded on 22-23 February. Engineers documented the multi-cavity magnetron, measured cavity geometry and magnetic field arrangements, and examined vacuum tube construction and pulse characteristics. Practical constraints became clear: precise machining, reliable high-vacuum assembly, and suitable magnetic and alloy materials were necessary for dependable operation, while wartime shortages and industrial disruption limited rapid replication. Bench tests and engineering reviews showed that the magnetron alone did not yield an operational centimetric force. Full performance depended on matched transmit, receive chains, appropriate antennas, plan position indicator displays, pulse modulators, production capacity, and tactical integration into night fighter procedures. System effectiveness also depended on antenna design, aircraft, altitude, and mission profile. German reverse engineering produced experimental centimetric devices in 1943–44, but these remained prototypes or limited trials and did not achieve production or deployment sufficient to overturn the Allies' centimetric advantage before the war ended. The H-2S radar salvaged from a short Stirling's wreckage near Rotterdam on the night of 2–3 February 1943 lay on Telefunken workbenches by late February. German engineers, assigned to assess its centimetric capability, measured the magnetron's cavity geometries, magnetic field arrangements, and vacuum tube construction with precision instruments. The cavity magnetron, operating at wavelengths around 10 centimeters, powered Royal Air Force Bomber Command's night operations by enabling ground mapping for navigation and target identification in darkness and adverse weather. German technical teams faced not only the complexity of this device, but also the constraints of a war-strained industrial base. The Stirling's wreckage had delivered a valuable example, but turning it into a fielded radar system required more than analytical insight. By March 1943, Telefunken staff had catalogued the magnetron's metallurgical and electrical properties, noting its reliance on high-purity metals and fine-tolerance machining. Each cavity demanded precision that exceeded what many wartime production lines could consistently achieve. The vacuum tube assembly, essential for stable high-power pulses, depended on high vacuum techniques and reliable glass and metal seals at a time when Allied bombing and resource pressures disrupted factory output. Engineers recorded the compact efficiency of the magnetic assemblies, but also recognized that competing demands from other weapon programs limited the availability of critical materials and specialized machine tools. The Luftwaffe's need for centimetric radar pressed against these material and production limits, and each test underlined the gap between laboratory work and large-scale manufacture. Work at Telefunken did not occur in isolation. Other German laboratories, including those at Siemens and AEG, contributed to magnetron and centimetric research, but coordination across firms and services remained uneven. In contrast, the captured H-2S set demonstrated a high degree of integration. The magnetron antennas, pulse modulators, and plan position indicator displays were designed to function as a coherent system aligned with Bomber Command's operational needs. Replicating this required more than copying a single component. It implied reorganizing parts of the radar development and production system under wartime pressure. By mid-1943, German engineers had produced experimental magnetrons and associated centimetric components, yet these remained laboratory or limited trial devices rather than fully fielded sets. The Luftwaffe sought prototypes for operational use, but shortages of materials, disruption of supply chains, and competing priorities slowed progress. Technical reports from these efforts acknowledged the magnetron's potential to transform night defense, while also emphasizing the practical difficulties of moving from captured example to series production. The tests of the captured cavity magnetron thus highlighted not only the sophistication of Allied radar engineering, but also the structural and industrial shortcomings that restricted German centimetric radar development during The cavity magnetron, extracted from the H-2S radar of a downed Stirling, demonstrated what German physicists already understood in theory about generating high-power centimetric waves, but it also underscored that converting this knowledge into a robust operational system would require far more than laboratory analysis. Testing highlighted three broad barriers. First, materials and manufacturing constraints made it difficult to machine the magnetron cavities, maintain the required vacuum, and ensure consistent output. Second, disrupted factories and dispersed production meant that even successful prototypes would be hard to build in quantity. Third, competing demands from other weapon and electronics programs pushed centimetric radar into the category of test or limited trial equipment rather than a fully fielded set. German technical reports from these tests acknowledged the potential of centimetric radar for night defense, but also underlined the practical obstacles to rapid deployment. Precision machining and vacuum integrity, both critical to magnetron performance, were difficult to sustain on disrupted wartime production lines. Material shortages and competing priorities constrained any shift toward large-scale centimetric manufacture. By autumn 1943, German engineers had gained a solid understanding of the captured cavity, magnetron's principles, and had produced experimental equipment. Yet, centimetric radar within the Luftwaffe remained, confined largely to development and trial use. The examination of the captured H-2S magnetron thus revealed not only the sophistication of Allied radar engineering, but also the structural and industrial shortcomings that restricted German centimetric radar development in Ichenjobaisishasan. The H-2S radar's cavity magnetron, captured from a short Stirling's wreckage near Rotterdam on the night of 2-3 February 1943, initially appeared to offer the Luftwaffe a path toward narrowing the technological gap. German engineers testing the device at wavelengths around 10 centimeters in Telefunken's laboratories confirmed its central role in Allied night operations, enabling ground mapping for navigation and target identification in darkness and adverse weather. By late 1943, however, the expectation of rapid replication had faded. Bench tests, thorough and sustained, showed that understanding the magnetron's operation did not by itself solve the wider industrial and organizational problems facing German radar development. The captured device, once viewed as a potential shortcut to parity, instead highlighted how much depended on the broader system that surrounded it. The magnetron's multi-cavity design, capable of producing high peak power pulses at around 10 centimeters, could be described and imitated on the drawing board, but sustaining those performance levels in series production demanded tight tolerances, rigorous quality control, and clear priority in resource allocation, making such coordination difficult to achieve quickly in Germany's late-war economy. As 1943 progressed, experimental centimetric radars built around the captured magnetron were tested on benches and in limited field trials. Yet they remained isolated projects that could not compensate for deeper structural constraints in production, logistics, and organization. By early 1944, the Luftwaffe's night defenses still relied primarily on metric and decimetric radars, such as Würzburg, despite the insights gained from H-2S, indicating that the bottleneck lay less in scientific understanding than in industrial capacity, coordination, and time. The H-2S radar's cavity magnetron, captured from a short Stirling's wreckage near Rotterdam, thus revealed not only the technical brilliance of Allied centimetric radar, but also the extent to which German limitations in production capacity and organizational coordination, rather than gaps in physics, constrained any response.